Good afternoon, everyone. I'm Mariam Sangi from UTM Maths Department. I'm working with Dr. Chok and Liu. It's my first time, so I'm sorry for if I make any mistake. It's really my first time for any presentation in a conference. So I will be presenting a new large eddy simulation model with anisotropic eddy viscosity based on Liutex vector. We will go through motivation and background, and then we will discuss about the limitations of eddy viscosity, Liutex concept, formulation for the model, and numerical validations, and then conclusion. So, generally, in large eddy simulations of turbulence flow, the large energy containing eddies are directly resolved, while the smaller scale eddies are missed by computational grids, which these unresolved motions influence the resolved flow field through additional stresses known as subgrid scale stresses. For the concept and definition of eddy viscosity, Dr. Yufi already discussed in detail for the filtering process of Navier-Stokes equation, which introduces the subgrid scale stress as follows, which is the average difference of average of uj subtract by average of ui, average of uj. So eddy viscosity is clear concept used to model the effect of unresolved turbulent motion on the resolved flow. And the total stress tensor is expressed as follows, in which the Vt is representing the eddy viscosity, and Sij is resolved strain tensor. Some limitations on the eddy viscosity. We believe that eddy has a direction, like if the momentum transfer is caused by unresolved eddies, then it's not isotropic. It has directional changes in every direction. It's not uniform. And also the grid is not uniform. We generally refine the grid in a certain direction, which we believe has some limitations. So for example, if we have a rotational axis to be z-axis, then the change occurs in x and y plane, which affect the equations for tau x y and tau y x, if we are talking about the z direction rotational. Based on these concepts, we enhance our equations for off-diagonal viscosity components, which capture the anisotropic rotational effect as follows. Tau xy, tau yz is given as if we add the effect of vector, if the rotation is at z-axis, then there is a change in xy direction. So the change is represented by delta x and delta y with the coefficient of, and this is the Liutex magnitude of Liutex vector in z direction. Similarly, if the rotation is at y direction, then the change occurs in z and x direction plane. So the change is represented by delta x and delta z in the equation of tau x z, tau z x. Also, if the rotational vector is in x direction, so we have a change in y and z direction, which is represented by delta y and delta z. So based on these formulations, we compare some results with the whale and without model and DNS, which shows a better improvement of proposed model. Like clearly we can see the proposed model has better results for the mean velocity curve, mean velocity profile. And we also compare the Reynolds stress result for U prime U prime, which hits the same level at the start for no model and whale, but it shows some improvement over here. I'm sorry, I forgot to post the grid, but the purple line shows the proposed model, and this line is representing no model, and the orange line is representing whale. Blue is DNS. Over here, same. In the starting, we have a proposed model goes a little bit higher, but over here it is delaying. And if we compare W prime, we have some improvement over here in the starting, which hits higher than no model and whale. For W prime, U prime, we have improvement here as well from whale and no model. We have improvement over here. And if we talk about the skin friction coefficient, it delays at the start, but it shows a good improvement over in this region. So if I conclude my presentation, then we can say that we are proposing to extend scalar to a vector quantity for the Liutex-based model. That's all. Any questions? I'm quite quick.